Vector is a matrix with a single column. Two examples of some vectors can be seen here. So you can see we use our standard matrix notation. We've got, sort of the brackets, the elongated brackets on each side, but we just have a single column. So we would read these as 1, 2, and 3, -1, 4, and 0, 5, 2, 7. And these examples are examples of vectors with 2, 3, and 4 components. So a vector with 2 components is called a two-dimensional vector. With 3 components, a three-dimensional vector. 4 components, a four-dimensional vector. And then in general, we might talk about an n-dimensional vector. We have the space Rn, which denotes the set of all n-dimensional vectors with real number components. Okay, so R2, that's all two-dimensional vectors. We saw some examples earlier. We could have, a two-dimensional vector 1, 5, for example. And then R3, that's all three-dimensional vectors. So we could have a three-dimensional vector 3, 4, -7. Vectors are commonly written using either bold letters when typed, so that's what you'll see in your book and maybe on some of your assignments. When we are handwriting vectors, it's hard to sort of bold our letters, so we would usually use this arrow notation. So some vectors in R2 written out, we might have u equals 1, 2, and v equals 3, -1. You can see the u using that bold notation, the v using that arrow notation. And we do want to, especially in this class, get used to using vector notation when we're writing out vectors. We're going to be doing, a lot of work this semester with vectors, and oftentimes we're going to have variables in the same equations or the same problems, where some of our variables will represent numbers, some will represent vectors, some might represent matrices. So it's going to be important for us to really differentiate when our variables are vectors versus some of these other objects. So we should get used to using this arrow notation anytime we are handwriting, a variable as a vector. If we're typing something up, then we can use either that bold or that arrow notation. Another thing we're going to be doing with vectors, specifically in R2 and R3, are visualizing them geometrically or graphing them. So vectors in R2 can be graphed as arrows in the plane. So for example, the vector 3, 2, we might graph as such. We've got a standard coordinate plane xy axes, and you can see that the first component of our vector u, which was 3, that tells us sort of how far we should go in the x direction. So we go 1, 2, 3 over in the x direction. And then the second component, in this case that's 2, tells us how far to go in the y direction. So 1, 2, and then we sketch our vector going, from the origin to the point 3, 2. Technically speaking, when we are talking about graphing vectors or visualizing vectors, they don't have to be drawn on a coordinate plane like this, starting at the origin and ending at the point given by the components. That is the standard way to, sketch a vector. But technically speaking, when we're sketching vectors, we really only care about kind of how far they move in each direction and not necessarily where they're starting and ending. So we don't even need to have a coordinate plane, but all things being equal, we will usually sketch vectors in this fashion where we start them at the origin and end them at the point given by each of those components. But there are certainly going to be situations where we're graphing vectors and we start them at a different point. And again, those are really technically the same vectors. So this vector 3, 2, for example, could start down here at the point -2, -2, and then we can sketch it in the same way by moving 3 over in the x direction, which would bring us over to the x coordinate of +1, and up 2 in the y direction. So that would bring us to the y coordinate of 0. So that would technically, give us this vector starting at, the same vector technically, but starting at this point down here, and then ending at this point up here. We can also graph vectors in R3. So that would be in three-dimensional space. So for example, the vector 2, 1, 3, again, we can graph this starting at the origin in 3 dimensions, 0, 0, 0. And then each component tells us how far to go in each direction. So an example might look something like this. Now, obviously, this image you're seeing is technically in 2 dimensions, but we are kind of trying to graph it out in 3 dimensions. So, hopefully this helps visualize what's going on there. We're moving, 2 coordinates or 2 units over in the x direction and one unit in the y direction to bring us in the xy plane to this point here, which is the point 2, 1 in the xy plane. And then we're going vertically up, in a sense, by 3 units in that z direction to get us up here to that the end point of that vector. And again, just like in R2, we can technically start these vectors anywhere we'd like, as long as we're moving in each direction by the prescribed amount. So we will do some graphing in certainly 2 dimensions and maybe a bit in 3 dimensions, but mostly focusing on 2 dimensions for this course. If you've already taken like a multivariable calculus course, you're probably comfortable with these concepts of graphing vectors, and in particular, kind of working in 3 dimensions. If you haven't taken a course like that, again, we're mostly going to be sticking with 2 dimensions. Vectors in dimensions higher than 3 cannot be physically graphed. So we couldn't, for example, do the same sort of graphing for a 4-dimensional or a 5-dimensional vector. However, it is still interesting and useful to think about higher dimensional vectors. Certainly algebraically, we would be working with higher dimensional vectors algebraically all the time, but even geometrically, again, you can kind of twist yourself in a pretzel trying to envision a 4 or 5-dimensional vector. But it is sort of an interesting thing to consider. We'll have some operations that we can do with vectors. So the first one we'll talk about is scalar multiplication. This is where we multiply a vector by a real number. And the way we do that is by multiplying each component of the vector by the scalar. So an example here, we could take the vector 1, -2, 4 and multiply it by the scalar. And by the way, when we say scalar here, we just are meaning a real number. We'll talk about where that term scalar comes from when we consider the geometry of this scalar multiplication in a little bit. But for now, just think of a scalar as a real number that we're multiplying by a vector. And you can see we just do that component by component. So 3 times 1 is 3, 3 times -2 is -6, and 3 times 4 is 12. And then the other operation is vector addition. And when we add 2 vectors, we just add the corresponding components. We can only add 2 vectors that are the same dimension. So we don't want to try and add, a 3-dimensional and a 7-dimensional vector together. That doesn't really make sense. So when we're talking about vector addition, it's always going to be 2 vectors that are the same dimension. So here are 2 3-dimensional vectors that we can add together, 1, 2, -1, plus 3, -4, 5. And so you can see 1 plus 3 is 4, 2 plus -4 is -2, -1 plus 5 is 4. And we're going to be considering in future video the kind of geometry of this idea of scalar multiplication and addition, specifically for R2, and certainly we could try and think about it for R3, but mostly for R2. What is happening on a graph when we scalar multiply or when we add two of these vectors?